Hello, beautiful human. It's your boy Chad, your interstellar guide through the most awe-inspiring wonders of the cosmos. Where are you watching from tonight? Are you tucked into bed, lounging on the couch? Maybe you've got headphones in, the lights are off, and you're ready to drift. Perfect. Because tonight, I'm taking you on a ride through the entire life cycle of a star. Birth, life, death, the whole saga. So settle in, relax, and let me walk you through one of the most incredible stories the universe has ever told. Have you ever looked up at the night sky and wondered what you're actually seeing? Those tiny pinpricks of light scattered across the darkness, they seem so permanent, so unchanging. You might see the same stars your grandparents saw, and their grandparents before them. It's easy to think of stars as eternal fixtures, like streetlights hanging in space. But they're not. Stars are born, they live, and they die. Every single one of them. The star you happen to glance at on a quiet evening might be in the middle of its life, steadily burning through its fuel, or it might already be dead, its light still traveling across the vastness of space, arriving at your eyes long after the star itself has ceased to exist. That's one of the strange and beautiful things about looking at the sky. You are, in a very real sense, looking backward in time. Tonight, we are going to trace the entire life cycle of a star. From the very first moment a cloud of gas begins to collapse under its own gravity, all the way to the spectacular endings that await different kinds of stars. Some stars end their lives quietly, fading into dim embers called white dwarfs. Others go out in unimaginable violence, exploding as supernovae and scattering their contents across the galaxy. And in the most extreme cases, some stars leave behind objects so dense and so strange that they warp the very fabric of space and time. The story of a star is also, in many ways, the story of everything around you. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of these elements were forged inside stars that lived and died long before our solar system existed. You are, in the most literal sense, made of stardust. That's not poetry, it's physics. To understand the life cycle of a star, we need to understand a few things first. We need to understand gravity, the force that pulls matter together and triggers the birth of a star. We need to understand nuclear fusion, the process that powers a star during its lifetime. And we need to understand the constant tension between these forces, a tug-of-war that determines when and how a star eventually meets its end. These ideas are not complicated. They follow from simple principles. But together, they produce some of the most dramatic and awe-inspiring events in all of nature. So let's begin at the very beginning. Let's go to the place where stars are born. Imagine a cloud, not the kind you see drifting across a blue sky on a summer afternoon, but something far larger, far colder, and far more diffuse. In the spaces between stars, there exist enormous clouds of gas and dust called nebulae. These are some of the most visually stunning objects in the universe. If you've ever seen photographs from the Hubble or James Webb space telescopes, you've probably seen nebulae, those vast, colourful, almost dreamlike structures stretching across light years of space. A nebula is primarily made of hydrogen, the simplest and most abundant element in the universe. Mixed in with the hydrogen, you'll find helium and trace amounts of heavier elements, things like carbon, oxygen, and silicon, remnants of stars that died before. There is also dust, tiny solid particles of various materials that scatter and absorb light, giving nebulae their rich and complex appearances. Some of the most famous nebulae have names you might recognize. The Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of the constellation Orion, is one of the closest and most active star-forming regions to Earth. Lying about 1,300 light-years away, the Eagle Nebula, home to the iconic pillars of creation photographed by Hubble, contains towering columns of gas and dust within which new stars are actively forming. The Carina Nebula, one of the largest and brightest nebulae in the sky, is a vast stellar nursery containing some of the most massive and luminous stars known. These nebulae are not rare or exotic. They are common features of spiral galaxies like our Milky Way, found primarily along the spiral arms where gas and dust are densest. Star formation is happening right now, at this very moment, in thousands of nebulae throughout our galaxy. Now, here is the key point. A nebula, left entirely to itself, would simply float there. The gas is spread so thinly that the gravitational pull between its particles is incredibly weak. On its own, it has no particular reason to do anything interesting. But the universe rarely leaves things entirely to themselves. Something has to disturb the cloud. Something has to give gravity a nudge. a reason to start pulling the gas together. This disturbance can come from many sources. Perhaps a nearby star explodes as a supernova, and the shock wave from that explosion ripples through the nebula, compressing regions of gas. Perhaps two galaxies pass close to each other, and the gravitational tides stir things up. Perhaps the nebula simply drifts into a denser region of the galaxy, where the surrounding pressure squeezes it from the outside. Whatever the cause, the effect is the same. A region of the cloud becomes just slightly denser than its surroundings, and once that happens, gravity takes over. This process was first described mathematically by the British physicist James Jeans in the early 20th century. In 1902, Jeans worked out the conditions under which a cloud of gas would become gravitationally unstable and begin to collapse. The critical factor is a balance between the cloud's internal pressure, which pushes outward and tries to keep the cloud expanded, and its gravitational pull, which draws everything inward. If the cloud is massive enough, or dense enough, or cold enough, gravity wins. The cloud begins to fall inward on itself. This threshold is known as the Jeans mass, and it marks the very first step on the road to becoming a star. Once the collapse begins, things start to change. As the gas falls inward, it compresses, and when gas compresses, it heats up. Think of a bicycle pump. When you push the handle down and compress the air inside, the pump gets warm. The same basic principle is at work here, just on a vastly larger scale. The falling gas converts gravitational energy into thermal energy, and the center of the collapsing region grows hotter and hotter. At this stage, the object is not yet a star. It is what astronomers call a protostar, a dense hot core embedded within a cocoon of gas and dust that is still raining down onto it. The protostar is luminous, but its light comes not from nuclear fusion. Not yet. It comes simply from the heat of compression, the energy released by all that material falling inward. Protostars can be hidden from view at visible wavelengths because of the thick envelope of dust surrounding them, but they shine brightly in infrared light, which can penetrate through the dust. This is one of the reasons the James Webb Space Telescope, with its powerful infrared instruments, has been so transformative for our understanding of star formation. It can peer into the hearts of nebulae and reveal the protostars forming within. The protostellar phase can last for hundreds of thousands of years, depending on the mass of the forming star. More massive protostars collapse faster, less massive ones take longer. During this time, the protostar may also develop a rotating disk of material around its equator, a protoplanetary disk, which is where planets can eventually form. So the birth of a star is often also the beginning of a planetary system. The process of star formation is not perfectly efficient. Not all the gas in a collapsing region ends up in the star. Some of it is flung outward in powerful jets that shoot from the poles of the protostar, perpendicular to the protoplanetary disk. These jets, called Herbig-Haro objects after the astronomers George Herbig and Guillermo Haro, who first studied them in the 1950s, can extend for light years and are among the most visually striking signs of active star formation. They carve through the surrounding nebula like cosmic fountains, glowing as they collide with the ambient gas. Stars also rarely form alone. Most stars are born in clusters, groups of dozens, hundreds, or even thousands of stars forming from the same parent cloud. Over time, these clusters disperse as the stars drift apart under the gravitational influence of the galaxy. But the stellar siblings can sometimes be traced back to their common origin. Our own sun was almost certainly born in such a cluster, roughly 4.5 billion years ago, but its siblings have long since scattered across the Milky Way. Eventually, the temperature at the core of the protostar reaches a critical threshold, roughly 10 million degrees Celsius. At this temperature, something remarkable happens. Hydrogen atoms are moving so fast, colliding so violently, that they overcome the natural electromagnetic repulsion between their positively charged nuclei and fuse together. 4 hydrogen nuclei combine to form one helium nucleus, and in the process, a small amount of mass is converted directly into energy, following Albert Einstein's famous equation, E=mc². This is nuclear fusion, and the moment it ignites in the core of a protostar, a star is truly born. The energy released by fusion creates an outward pressure, a radiation pressure, that pushes against the inward pull of gravity. For the first time, the collapsing object reaches a state of equilibrium. Gravity pulls inward, fusion pushes outward, and the two forces balance each other. The star stabilizes. It stops collapsing. It begins its long, steady life on what astronomers call the main sequence. The main sequence is the longest and most stable phase of a star's life. It is the period during which a star steadily fuses hydrogen into helium in its core, producing energy at a consistent rate and shining with a relatively constant brightness. Our own Sun is a main sequence star, and it has been one for about 4.5 billion years. It will continue to be one for roughly another 5 billion years. That is a long, quiet, productive life. But not all main sequence stars are the same. Stars come in a tremendous range of sizes, temperatures, and luminosities, and these properties are almost entirely determined by one thing: mass. The mass of a star at its birth dictates nearly everything about its life: how hot it will be, how brightly it will shine, what color it will appear, how long it will live, and ultimately, how it will die. This relationship was first mapped systematically by two astronomers working independently in the early 20th century. Ejnar Hertzsprung, a Danish chemist turned astronomer, and Henry Norris Russell, an American astronomer at Princeton. Each developed diagrams that plotted stars according to their brightness and temperature. When they did this, they discovered that most stars fall along a diagonal band, a sequence. This is the main sequence, and the diagram is known as the Hertzsprung-Russell diagram, or HR diagram. It remains one of the most important tools in all of stellar astronomy. The pattern the HR diagram reveals is profound. The most massive stars sit at the upper left of the diagram. They are extremely hot, extremely luminous, and they glow with a blue or blue-white light. The least massive stars sit at the lower right. They are cool, dim, and they glow with a deep red color. Our Sun sits somewhere in the middle, a yellow star of moderate temperature and moderate brightness. Now here is something that might seem counterintuitive. You might expect that a more massive star, with more fuel available, would live longer. After all, if you have a bigger gas tank, shouldn't you be able to drive farther? But that's not how it works with stars. Massive stars burn through their fuel at a phenomenally faster rate than smaller stars. A star 10 times the mass of the Sun doesn't live 10 times as long. It lives roughly 1,000 times shorter. A truly massive star might exhaust its hydrogen fuel in just a few million years, while a small red dwarf star, with perhaps 1/10 the mass of the Sun, could continue burning for trillions of years, far longer than the current age of the universe. Think of it this way. Imagine two candles. One is a small tea light, and the other is a massive bonfire. The bonfire has far more fuel, but it burns so intensely that it's gone in hours. The tea light, burning its tiny flames slowly and patiently, can last all night. Stars work the same way. The smallest stars on the main sequence are the red dwarfs. These are stars with less than about half the mass of the Sun. They are by far the most common type of star in the universe. In fact, roughly 70 to 80% of all stars in the Milky Way are red dwarfs. They are cool, with surface temperatures around 3,000 to 4,000 degrees Celsius, and they glow with a dim red light. Many are so faint that they are invisible to the naked eye. Even though some of them are among our nearest stellar neighbors, Proxima Centauri, the closest star to our Sun at just over 4 light-years away, is a red dwarf. Despite being so close in astronomical terms, it is far too dim to see without a telescope. Red dwarfs are miserly with their fuel. They burn hydrogen so slowly and so efficiently that they can persist for tens of billions, even trillions of years. The universe is currently about 13.8 billion years old. That means every red dwarf that has ever been born is still burning today. Not a single one has yet reached the end of its life. We have never observed a red dwarf die of old age, and we won't for a very long time. At the other extreme are the blue giants and supergiants, the most massive and luminous stars on the main sequence. Stars like Rigel, the blue supergiant that marks Orion's foot, are tens of thousands of times more luminous than the Sun. They have surface temperatures exceeding 20 or 30,000 degrees Celsius, giving them their characteristic blue-white appearance. These are the rarest of stars, making up only a tiny fraction of the stellar population, but they dominate the appearance of the night sky because of their extreme brightness. You can see them across vast distances. These massive stars live fast and die young. A star of 30 solar masses might spend only 5 to 10 million years on the main sequence before exhausting its fuel. Compare that to a red dwarf, which will still be quietly burning when the universe is 100 times its current age. The differences in stellar lifetimes are staggering. During the main sequence phase, the star is in a state of hydrostatic equilibrium. This is a fancy term for a simple idea. Every layer of the star is balanced. The weight of the material above any given layer pushes inward, and the pressure from the hot gas and radiation below pushes outward. These forces match precisely. The star is neither expanding nor contracting. It simply exists, burning its fuel and radiating energy into space. The energy produced in the core must travel outward to the surface before it can escape into space as light. In the inner regions of a star like the Sun, this transport happens through radiation. Photons of light are emitted by the hot core, but they don't travel in a straight line. They are absorbed and re-emitted by the dense plasma around them, bouncing randomly in all directions. A single photon can take tens of thousands of years, some estimates suggest hundreds of thousands, to random walk its way from the core to the outer layers of the Sun. Think about that. The sunlight warming your face today was generated in the Sun's core, long before recorded human history began. In the outer layers of many stars, energy transport switches from radiation to convection. Hot plasma rises toward the surface, cools, and sinks back down, much like a pot of water heating on a stove. If you could see the surface of the Sun up close, you would see a granular boiling pattern called granulation, the tops of convection cells where hot gas is rising. Each of these granules is roughly the size of a large country on Earth. The astronomer who perhaps did more than anyone to explain the internal structure and energy production of stars was Arthur Eddington. In the 1920s, Eddington proposed that stars are powered by the fusion of hydrogen into helium. This was before the detailed nuclear physics was worked out, but Eddington's insight was correct. He famously said that if someone pointed out that the stars were not hot enough for nuclear reactions, his response would be to tell them to go and find a hotter place. Eddington understood, even before the precise mechanisms were known, that the immense temperatures inside stars made nuclear fusion not only possible, but inevitable. The detailed physics of stellar fusion were later worked out by Hans Bethe, a German-American physicist, in 1939. Bethe described two main cycles by which hydrogen is converted to helium inside stars. In lower-mass stars like the Sun, the dominant process is the proton-proton chain, a series of reactions in which hydrogen nuclei gradually combine to form helium. In more massive, hotter stars, the dominant process is the CNO cycle, which uses carbon, nitrogen, and oxygen as catalysts to achieve the same result. Bethe received the Nobel Prize in Physics in 1967 for this work. Nothing lasts forever. Eventually, after millions or billions of years on the main sequence, a star begins to run out of hydrogen fuel in its core. What happens next depends, once again, almost entirely on the star's mass. But in all cases, the departure from the main sequence marks the beginning of the end. Let's start with a star like our Sun, a star of modest mass. When the hydrogen in its core is finally exhausted, the core is left as a dense ball of helium. Fusion stops in the core. Without the outward pressure of fusion to counteract gravity, the core begins to contract. As it contracts, it heats up, and this heat radiates outward, warming the layers of hydrogen that surround the core. Something interesting happens. The shell of hydrogen just outside the core becomes hot enough to ignite fusion. Hydrogen begins fusing in a shell around the inert helium core. This shell burning actually produces more energy than the original core fusion did, and the extra energy causes the outer layers of the star to expand enormously. The star swells, growing to many times its previous size. At the same time as the outer layers expand, they cool, and the star's surface temperature drops. It shifts from yellow or white to a deep orange or red. The star has become a red giant. When our Sun reaches this stage, roughly 5 billion years from now, it will expand to engulf the orbits of Mercury and Venus, and possibly Earth as well. Even if Earth narrowly escapes being swallowed, the intense heat from the bloated Sun will boil away the oceans and strip away the atmosphere. It will not be a pleasant time to live in this neighborhood. The red giant phase is unstable. The helium core continues to contract and heat up, and eventually, it reaches a temperature of about 100 million degrees Celsius. At this point, helium nuclei, which are much heavier and more positively charged than hydrogen nuclei, can overcome their mutual repulsion and begin to fuse. 3 helium nuclei combine to form one carbon nucleus, in a process called the triple alpha process. The discovery of the triple alpha process has a fascinating story behind it. In the early 1950s, the astronomer Fred Hoyle realized that for carbon to exist in the universe in the quantities we observe, the triple alpha process must have a specific resonance, a quantum mechanical property that greatly enhances the probability of the reaction. Hoyle predicted this resonance based purely on the fact that carbon exists, a remarkable example of using an observed result to deduce fundamental physics. The resonance was later confirmed experimentally by William Fowler and his colleagues at Caltech. This so-called Hoyle state of the carbon-12 nucleus is one of the most celebrated predictions in nuclear astrophysics. For a star like the Sun, helium burning in the core produces carbon and some oxygen, but the star's mass is not sufficient to raise the core temperature high enough to fuse these heavier elements. So once the helium is exhausted, that's effectively the end. The core, now made primarily of carbon and oxygen, contracts one final time. The outer layers of the star, loosely bound after the red giant phase, are gently expelled into space, forming a beautiful glowing shell of gas called a planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. The term was coined by William Herschel in the 18th century because through the small telescopes of his era, these round, glowing objects looked a bit like the disks of planets. The name stuck, even though we now know exactly what they are, the shed outer layers of dying stars. Some planetary nebulae are extraordinarily beautiful. The Ring Nebula in the constellation Lyra, the Helix Nebula sometimes called the Eye of God, the Cat's Eye Nebula, with its intricate concentric shells. These are among the most photographed objects in the sky. They glow because the ultraviolet radiation from the hot central white dwarf ionizes the expanding gas, causing it to fluoresce in vivid colors. Each planetary nebula is unique, shaped by the particular history of the star that created it, including its rotation, magnetic field, and whether it had a companion star. Planetary nebulae are relatively short-lived on cosmic timescales. They persist for perhaps 10 to 20,000 years before dissipating into the interstellar medium. That is a blink of an eye compared to the billions of years the star spent on the main sequence. But during that brief time, they are returning processed material to the galaxy, enriching it with carbon, nitrogen, and oxygen. At the center of the planetary nebula sits the exposed core of the star, a white dwarf. This is an extraordinarily dense object, roughly the mass of the Sun compressed into a volume about the size of Earth. A teaspoon of white dwarf material would weigh several tons. The white dwarf no longer produces energy through fusion. It simply glows from residual heat, slowly cooling over billions of years, eventually fading to a cold, dark object, sometimes called a black dwarf. However, the universe is not yet old enough for any white dwarfs to have cooled to this point. Every white dwarf that has ever formed is still glowing, at least faintly. The physics that keeps a white dwarf from collapsing further was explained by Subrahmanyan Chandrasekhar, an Indian-American astrophysicist, in the 1930s. Chandrasekhar showed that in a white dwarf, the inward pull of gravity is balanced not by fusion, but by a quantum mechanical effect called electron degeneracy pressure. This is a consequence of the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. When the electrons in the white dwarf are packed so closely together that they resist further compression through this quantum mechanical rule, the star stabilizes. But Chandrasekhar also showed that this support has a limit. If the mass of the white dwarf exceeds about 1.4 times the mass of the Sun, electron degeneracy pressure is not strong enough to hold it up. This threshold is called the Chandrasekhar limit. It earned Chandrasekhar the Nobel Prize in Physics in 1983, nearly 50 years after his original calculations, a long overdue recognition. His work was initially dismissed by the prominent astronomer Arthur Eddington, who found the implications troubling. The two had a famous public disagreement, but time and observation proved Chandrasekhar right. Now let us turn to the fate of more massive stars, those born with perhaps 8 or more times the mass of the Sun. Their lives are shorter, more dramatic, and their deaths are among the most violent events in the cosmos. A massive star races through its hydrogen supply on the main sequence in just a few million years. When the hydrogen in its core is exhausted, the same basic process we described earlier begins. The core contracts, heats up, and a shell of hydrogen ignites around it. The star expands into a supergiant, a truly enormous object. If you placed a red supergiant like Betelgeuse, the bright star marking Orion's shoulder, at the center of our solar system, its surface would extend beyond the orbit of Jupiter. But unlike a Sun-like star, a massive star doesn't stop at helium fusion. Its core is so massive, and gravity compresses it so powerfully, that it can reach the temperatures necessary to fuse heavier and heavier elements. After helium fuses into carbon, the core contracts again, heats up again, and carbon begins to fuse. Carbon fusion produces neon, magnesium, and sodium. Then neon fuses, then oxygen, then silicon. Each successive stage of fusion produces heavier elements and requires higher temperatures. Each stage also lasts for a shorter period of time. While hydrogen burning lasted millions of years, helium burning might last hundreds of thousands. Carbon burning might last a few hundred years, neon burning, a single year, oxygen burning, a few months, and silicon burning, the final stage, lasts only about a day. If you could somehow slice the star open at this point, you would see a layered structure, like an onion. The outermost layers are still hydrogen. Beneath that, a shell of helium, then carbon, then neon, then oxygen, then silicon, and at the very center, the final product of silicon burning, iron. Iron is the end of the line. This is because iron has the most tightly bound nucleus of any element. Fusing iron into heavier elements does not release energy. Instead, it requires energy. It is an endothermic reaction. So when the core of the massive star fills with iron, fusion simply stops. There is no more energy to be extracted. The outward pressure that has supported the star against gravity for its entire life suddenly vanishes. And then, in less than a second, catastrophe strikes. The iron core, no longer supported by fusion energy, collapses under its own gravity. It doesn't collapse slowly. It collapses at a significant fraction of the speed of light. In roughly a quarter of a second, a core that was roughly the size of Earth compresses to a ball just 10 to 20 kilometers across. The density in this collapsing core reaches values that are almost impossible to comprehend, several 100 million tons per cubic centimeter. The collapse is halted by nuclear forces, the strong nuclear force between protons and neutrons that resists further compression. The infalling material slams into this suddenly rigid core and bounces. A shockwave forms and races outward through the star. At the same time, the extreme conditions in the core trigger a flood of neutrinos, ghostly subatomic particles that barely interact with matter. Under normal circumstances, neutrinos pass through the entire star as if it weren't there. But the densities here are so extreme that even neutrinos are briefly trapped, and when they escape, they carry away an enormous amount of energy. In fact, roughly 99% of the total energy of the explosion is carried away by neutrinos. Only about 1% goes into the visible explosion, the light and the blast wave that we observe. And yet that 1% is still enough to briefly outshine an entire galaxy. This is a supernova. Specifically, this type of explosion, triggered by the collapse of a massive star's core, is called a core collapse supernova, or a Type II supernova. It is one of the most energetic events in the universe. The physics of how exactly the shockwave manages to blow the star apart is still an active area of research. For decades, computer simulations showed that the shockwave alone was not powerful enough. It would stall partway through the star, losing energy as it plowed through the dense outer layers. The neutrino-driven mechanism, first proposed by Sterling Colgate and Richard White in the 1960s, and later refined by James Wilson in the 1980s, suggests that the intense neutrino flux re-energizes the stalled shockwave, giving it the extra push needed to tear the star apart. Modern simulations running on the world's most powerful supercomputers have confirmed that this mechanism can work, though the details are still being refined. The supernova explosion scatters the star's outer layers into space at speeds of thousands of kilometers per second. And here is something crucial. The extreme temperatures and pressures during the explosion itself forge elements heavier than iron, things like gold, silver, platinum, uranium, and many others. These elements can only be created in the intense conditions of a supernova or similar cataclysmic events like neutron star mergers. So every atom of gold in every ring, every necklace, every Olympic medal was born in the death throes of a massive star or in the collision of the remnants it left behind. Supernovae have been observed by humans throughout history, though they were not always understood. In 1054, Chinese and Japanese astronomers recorded the appearance of a bright new star, so brilliant it was visible in broad daylight for several weeks. That object was a supernova, and its remnant is what we now call the Crab Nebula, one of the most studied objects in the sky. In 1572, the Danish astronomer Tycho Brahe observed another supernova, which challenged the prevailing Aristotelian view that the heavens were unchanging and perfect. Just 32 years later, in 1604, Johannes Kepler observed yet another, the last supernova to be seen with the naked eye in our own galaxy. We are, by historical standards, overdue for another. The most recent nearby supernova occurred in 1987, not in the Milky Way but in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, designated supernova 1987A. It was the closest supernova observed since the invention of the telescope. For the first time, astronomers were able to study a supernova in real time with modern instruments. And critically, neutrino detectors in Japan and the United States detected a burst of neutrinos from the event, arriving just hours before the visible light. This was a triumphant confirmation of the theoretical models predicting that neutrinos carry away most of the energy in a core collapse supernova. The detection of those 25 neutrinos, out of the estimated 10 to the power of 58 that the supernova produced, opened the era of neutrino astronomy. The expanding cloud of debris from a supernova is called a supernova remnant. Over thousands of years, it spreads out and mixes with the surrounding interstellar medium, enriching it with heavy elements. These enriched clouds of gas can then be disturbed and compressed, starting the cycle again, giving birth to a new generation of stars, and perhaps new planets, and perhaps, eventually, new life. This is the great cycle of stellar evolution. Stars are born from the ashes of dead stars. The universe recycles its material, building ever more complex structures with each generation. What about the core that was left behind when the massive star exploded? Its fate depends on how much mass remains after the supernova. If the remaining core is between roughly 1.4 and about 2 to 3 solar masses, it settles into an exotic state called a neutron star. In a neutron star, the protons and electrons have been squeezed together by the immense pressure, merging to form neutrons. The entire object is essentially a single giant atomic nucleus, about 20 kilometers across, yet containing more mass than the Sun. A teaspoon of neutron star material would weigh about 1 billion tons. Neutron stars were first predicted theoretically by Walter Baade and Fritz Zwicky in 1934, just 2 years after James Chadwick discovered the neutron. Baade and Zwicky proposed that supernovae could produce these incredibly dense stellar remnants. Their prediction was largely ignored or considered exotic for over 3 decades. Then, in 1967, a graduate student named Jocelyn Bell Burnell, working at Cambridge under the supervision of Anthony Hewish, discovered a strange pulsating radio signal from space. The signal was remarkably regular, pulsing once every 1.337 seconds. At first, the team jokingly labeled the source LGM-1, for Little Green Men, wondering if it could be an artificial signal from an alien civilization. But soon more sources were found, and it became clear that these were natural objects. They were pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like lighthouse beams, and if one happens to point at Earth, we detect a pulse. Some pulsars spin incredibly fast. The fastest known pulsar rotates over 700 times per second. Imagine an object more massive than the Sun, compressed to the size of a city, spinning hundreds of times every second. The surface is moving at a significant fraction of the speed of light. The magnetic field is trillions of times stronger than Earth's. Neutron stars are among the most extreme objects in the known universe. The surface of a neutron star is equally remarkable. It is thought to consist of a solid crystalline crust of iron nuclei, incredibly rigid and yet incredibly thin relative to the star's radius. Beneath this crust lies a sea of neutrons in a superfluid state, flowing without friction. At the very core, the conditions are so extreme that physicists are uncertain what state of matter exists there. It may be ordinary neutrons, or it may be something more exotic, perhaps a quark-gluon plasma in which the neutrons themselves have been broken down into their constituent quarks. Neutron stars can also occur in binary systems, orbiting alongside another star. In some cases, the neutron star can accrete matter from its companion, and this matter, falling onto the surface, can trigger thermonuclear explosions called X-ray bursts. In the most dramatic cases, 2 neutron stars in a binary system can spiral inward toward each other, losing energy by emitting gravitational waves, the ripples in space-time predicted by Einstein's general theory of relativity. Eventually, they collide and merge in a cataclysmic event called a killer nova. In 2017, the LIGO and Virgo gravitational wave observatories detected gravitational waves from such a merger for the first time, designated GW17 Dodlon. Telescopes around the world also observed the event in visible light, radio waves and other wavelengths. This was a watershed moment in astronomy, the beginning of multi-messenger astrophysics, observing the same event through both gravitational waves and electromagnetic radiation. The merger was also confirmed to produce enormous quantities of heavy elements like gold and platinum, providing direct evidence for how these elements are created in the universe. But there is something even more extreme. If the remaining core after a supernova exceeds roughly 2 to 3 solar masses, not even the repulsive force between neutrons, a quantum mechanical effect called neutron degeneracy pressure, can halt the collapse. There is nothing left to resist gravity. The core collapses without limit, compressing down to a single point of theoretically infinite density, a singularity. What forms is a black hole? The concept of an object so dense that nothing, not even light, could escape from it, was first suggested by the English clergyman and natural philosopher John Michell in 1783. Michell imagined what he called dark stars, bodies whose gravitational pull was too strong for light to break free. The idea was largely forgotten until Albert Einstein published his general theory of relativity in 1915. Just months later, the German physicist Karl Schwarzschild, while serving on the Eastern Front during World War I, found the first exact solution to Einstein's field equations. This solution described the space-time geometry around a non-rotating spherical mass, and it revealed the existence of a critical radius, now called the Schwarzschild radius, at which the escape velocity equals the speed of light. Anything crossing this boundary, known as the event horizon, is trapped forever. Schwarzschild's solution was initially considered a mathematical curiosity. Many physicists, including Einstein himself, doubted that such objects could actually form in nature. It was not until the work of physicists like Roger Penrose in the 1960s that the theoretical inevitability of black hole formation was rigorously established. Penrose proved that once a star collapses past a certain point, the formation of a singularity is inevitable under the laws of general relativity. For this work, Penrose was awarded the Nobel Prize in Physics in 2020. Black holes are invisible by definition, since light cannot escape from them, but they can be detected indirectly. When matter falls toward a black hole, it forms a swirling disk of superheated gas called an accretion disk, which radiates intensely in X-rays before crossing the event horizon. Black holes in binary systems, where they orbit alongside a normal star, can strip gas from their companion, and this gas forms a visible accretion disk. The first strong black hole candidate, Cygnus X1, was identified in this way in the early 1970s. In April 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy Messier 87. The image showed a bright ring of superheated gas surrounding a dark central region, the shadow of the event horizon. It was a stunning confirmation of a prediction made over a century earlier. The black hole at the center of M87 is a true monster, containing about 6.5 billion times the mass of our Sun. Its event horizon is larger than the entire solar system. In 2022, the same collaboration released an image of the supermassive black hole at the center of our own Milky Way galaxy, called Sagittarius A star. This black hole is much smaller, about 4 million solar masses, but it is much closer to us, lying roughly 26,000 light-years away at the heart of the galaxy. The image confirmed decades of indirect evidence that a supermassive black hole lurks at the center of our galaxy. These supermassive black holes are a different category from the stellar mass black holes produced by supernovae. They contain millions or billions of times the mass of the Sun, and they sit at the centers of most, if not all, large galaxies. How they formed and grew so massive remains one of the great open questions in astrophysics. They may have started as the remnants of the first generation of extremely massive stars, and then grown through mergers and accretion over billions of years, or they may have formed through some other mechanism entirely. What is certain is that black holes, despite their name and reputation, are not cosmic vacuum cleaners. They do not reach out and suck in distant objects. Outside their event horizons, they behave gravitationally just like any other object of the same mass. If the Sun were magically replaced by a black hole of the same mass, Earth would continue to orbit exactly as before. It would be dark and cold, certainly, but we would not be sucked in. Black holes are only dangerous if you get too close. Let us step back now and consider what we have covered. We began with a cloud of gas, drifting quietly in the space between stars. We watched gravity gather that gas, compress it, heat it, until nuclear fusion ignited and a star was born. We traced the long, stable life of a star on the main sequence, the careful balance between gravity and radiation pressure. We saw what happens when the fuel runs out, how sun-like stars swell into red giants, shed their outer layers, and leave behind white dwarfs. And we followed the dramatic fate of massive stars, through the onion-like layers of successive nuclear burning, to the catastrophic core collapse and the brilliant explosion of a supernova, leaving behind neutron stars or black holes. This is not just a story about distant objects in space. It is, in the deepest sense, our story. The elements that make up your body were forged in the cores of stars that lived and died before the Sun was born. The iron in your hemoglobin, the molecule that carries oxygen through your blood, was produced in the core of a massive star. The carbon that forms the backbone of every organic molecule in your body was made through the triple alpha process in the heart of a red giant. The oxygen you are breathing was produced by nuclear fusion in a star that no longer exists. We are connected to the stars in the most intimate and material way possible. We are not merely observers of the cosmos. We are participants in it. We are the cosmos observing itself. And the cycle continues. Right now, in nebulae across the Milky Way and in galaxies throughout the universe, new stars are being born. Some of them will be small and dim, burning quietly for trillions of years. Some will be massive and brilliant, blazing through their fuel and dying in spectacular explosions within a few million years. And when they die, they will seed the interstellar medium with the heavy elements necessary for new stars, new planets, and perhaps new life. Have you ever noticed how a garden works? You plant a seed, it grows, it flowers, it produces new seeds, it dies, and from those seeds, new plants grow. The cycle repeats, each generation building on what came before. Stars work the same way. Each generation of stars enriches the raw materials of the universe, making it possible for the next generation to produce more complex chemistry, more intricate worlds. The first generation of stars, born from the primordial hydrogen and helium of the Big Bang, contained no heavy elements at all. They could not have formed rocky planets. They could not have given rise to life as we know it. But when they died, they seeded the universe with carbon, oxygen, silicon, iron, and dozens of other elements. The next generation of stars formed from this enriched material, and they could host planets with solid surfaces, with water, with complex chemistry. Our Sun is a third-generation star, or perhaps even later. It formed from a cloud that had been enriched by many generations of stellar death and rebirth. The diversity of elements in our solar system, the rocky inner planets, the gas giants, the icy moons, the asteroids and comets, all of this complexity is a direct inheritance from the stars that came before. Consider how remarkable that inheritance is. The silicon in the glass of your window, the aluminum in the frame of your phone, the phosphorus in your DNA. None of these elements existed in the early universe. They were all manufactured inside stars. The universe began with almost nothing but hydrogen and helium, the two simplest elements, and through billions of years of stellar alchemy, generation after generation, it built up the entire periodic table. Every element heavier than helium was created by a star, every single one. And there is something else worth reflecting on. The fact that we can understand any of this at all, that beings made of stardust, living on a small rocky world, orbiting an ordinary star in an ordinary galaxy, can look outward and piece together the story of how stars live and die. We can measure the temperature of a star thousands of light years away. We can determine its chemical composition from the light it emits. We can calculate how long it will live and predict how it will die. This understanding, built up over centuries by countless astronomers, physicists, and mathematicians, is itself one of the great achievements of the matter that stars have produced. So the next time you look up at the night sky, consider that you are looking at a living process. The stars are not just points of light. They are engines of creation, the forges in which the raw materials of existence are shaped and reshaped, generation after generation. Every star you see is somewhere on this journey, being born, living its life, or approaching its end. And somewhere out there, in a cloud of gas and dust that you cannot see, the next generation of stars is already beginning to form. The universe is patient. It works on timescales that dwarf human comprehension. But its processes are elegant, and they are, at their core, simple. Gravity pulls things together, pressure pushes things apart, and in the space between those two forces, stars are born, stars live, and stars die. And from their deaths, new stars, new worlds, and new possibilities emerge. Let that thought settle. Let it drift through your mind as your eyes grow heavy and your breathing slows. You are made of stars. You are part of this great cycle, and the universe, in all its vastness and all its silence, is still at work, still creating, still unfolding, moment by moment, in the darkness between the stars.